Now, this is a little more intimidating looking absolute value equation, because the expression that's in the absolute value expression is a quadratic expression, rather than being a linear expression as we saw in the previous videos. This says the absolute value of x squared minus 2x is supposed to equal 3. That doesn't stop my technique, though. It still has to be true that if the absolute value of this quantity is 3, then this quantity, x squared minus 2x, is either equal to 3, or the quantity, x squared minus 2x, would have to be negative 3, wouldn't it? The only two values that have an absolute value of 3 are 3 and negative 3. So x squared minus 2x must either be 3, or x squared minus 2x must be equal to negative 3. And now, instead of creating linear equations to solve, I've created quadratic equations to solve. So let's put them in standard form and see what we can do with them. We'll solve them one at a time. So I'll subtract 3 from both sides, putting it in standard form. That's a pretty simple looking trinomial. Perhaps it's factorable. In fact, when you solve a problem like this, you probably want to check to see if your trinomial is factorable, rather than automatically jumping into the quadratic formula. Chances are it's going to be a factorable polynomial, and probably won't be too difficult a one to factor, even if you're not that good at factoring. X times x would make x squared. To make a minus 3, you got to have a plus and a minus, haven't you? And the way to make a 3 is with a 3 and a 1, and I can make a 2, and I can make a minus 2 if I make it x minus 3 and x plus 1. Because this would give me plus 1x for the O of FOIL, minus 3x for the I of FOIL, those combine to minus 2x. So there's my factorization of that trinomial, and from that factorization I can conclude that x equals 3 or x equals negative 1, right? As what you've always done when you solved quadratic equations by factoring. Well, let's see if we can solve the other quadratic equation. We need to add 3 to both sides to put this equation in standard form. And let's see if we can solve this equation also by factoring. I'm not sure that one looks too good to solve by factoring. I would have to have, in order to have a plus here and a minus here, I'd have to have two minuses. And I don't think I can factor that. The only factorizations are 1 and 3, and that's not going to make a 2. That would make a minus 4. So that equation's not solvable by factoring. So we would have to solve this equation using the quadratic formula. So let's take a look at doing that, just to remind ourselves how to solve a quadratic equation with the formula. It's in standard form, so we'd have x equals the opposite of b, so that would be 2, plus or minus the square root of the square of b, minus 4 times a. The a value is 1, the c value is 3. All of that over 2 times a. So we have x equals 2 plus or minus the square root of, the square of negative 2 is 4, minus 4 times 3 is 12, all of that over 2. So x equals 2 plus or minus the square root of negative 8 over 2. Oh, the square root of negative 8 tells us we have two complex number solutions. So our first equation gave us two real number solutions, and now this second equation is going to give us two complex number solutions. So we had solutions, well, I think our solutions from the first equation were x equals 3 and x equals negative 1, and these are going to be two complex number solutions. Let's see if we can simplify the square root of negative 8. That's the square root of 4 times the square root of 2 times the square root of negative 1, isn't it? 8 can be broken down into 4 times 2, 4 being a perfect square. We can handle the square root of the negative with square root of negative 1, which we use the lowercase letter I. And then remember, we always write complex number solutions as the two separate fractions, the two separate portions of a complex number. So I'm going to divide both those terms by 2. 2 divided by 2 gives me 1. 2 divided by 2 gives me 1, which 1 times the square root of 2 is just the square root of 2. So this original absolute value equation had 2 real solutions and 2 complex number solutions. And I used my same technique to solve it that I had used on the previous absolute value equation.